Chapter 8, Module 1. In this module, we shall discuss geometric simplex and simplicial complex. We shall see that there are several topological spaces which have simplicial structure. What do we mean by simplicial structure will be formalized in this module. We shall discuss or define triangulation of topological spaces and simplicial complex later on. But in this module, we develop the prerequisites for doing so. We start with defining geometrically independent points. Suppose a set of k plus 1 points a0, a1, ak is given. This set of points is said to be geometrically independent if we construct the set a1 minus a0, a2 minus a0 up to ak minus a0 and see that this set is linearly independent in Rn. Now, this definition is valid for k greater than or equal to 2. If we take a set of a single point, that is a singleton, then it is always geometrically independent by definition. Now, this definition does not depend on the chosen point a0. In other words, if we take the set a1 minus a0 to ak minus a0, then this set is linearly independent if and only if aj minus ai, when j varies from 0 to k, j not equal to I, this particular set is linearly independent for each I equal to 0 to k. Now, let us just see that it is always known that any one dimensional subspace of Rn is represented by a straight line passing through origin. So, any straight line in Rn can be viewed as a translet of the one dimensional subspace parallel to it. That is, any straight line in Rn is a coset of the form x plus v1, where v1 stands for a one dimensional subspace of Rn and x is any point in Rn. Similarly, any two dimensional subspace of Rn is represented by a plane passing through origin. That is, a plane in Rn is a coset of the form x plus v2, where x is a point in Rn and v2 is a two dimensional subspace of Rn. Therefore, if we generalize this concept, we get the definition of k-dimensional hyperplane in Rn. The definition says that a k-dimensional hyperplane in Rn is a coset of the form x plus vk, where x is some point in Rn and vk is a k-dimensional subspace of Rn. That is, hk is x plus vk for some point x belonging to Rn. Now, we observe a few facts. First of all, if we take a set of 2 points a0 and a1, then it is always geometrically independent, because whenever we take the set a1 minus a0, it is a set consisting of a single point and that is a non-null vector in Rn. So, it is always linearly independent. Now, if we take a set of 3 points a0, a1 and a2, then for geometrical independence of this set, we need the set a1 minus a0 and a2 minus a0, the set consisting of two vectors, to be linearly independent. But linear independence of two vectors is nothing but non-collinearity of the points a0, a1 and a2. Similarly, if we take a set of 4 points a0, a1, a2, a3, it is geometrically independent if and only if the points a0, a1, a2, a3 are non-coplanar. So, from these observations, we see that there is no one dimensional hyperplane containing 3 points, there is no two dimensional hyperplane containing 4 points. So, we generalize this fact and get the theorem that if a set of k plus 1 points are given, then this set of points is geometrically independent if and only if there does not exist any k minus 1 dimensional hyperplane containing this set. Let us try to prove this. Suppose A0, A1, Ak be geometrically independent in Rn, where k is greater than equal to 2. If possible, let us assume that there is a k minus 1 dimensional hyperplane Hk minus 1 containing the set. Then Hk minus 1 is equal to x plus Vk minus 1 for some x belonging to Rn and k minus 1 dimensional subspace Vk minus 1 of Rn. So, Ai minus x belongs to Vk minus 1 for I equal to 0 to k. That is, Ai minus A0 is Ai minus x minus A0 minus x, which is a point in Vk minus 1, because Vk minus 1 is a k minus 1 dimensional vector space, which is not possible. Conversely, suppose this set A0 to Ak is geometrically dependent in Rn. So, A1 minus A0 to Ak minus A0, this particular set capital A is linearly dependent. Then the dimension of the linear span of A is at most k minus 1. Hence, one may obtain a vector space Vk minus 1 of dimension k minus 1 containing the set A. That is, Ai minus A0 belongs to Vk minus 1 for each I equal to 1 to k, and consequently Ai belongs to A0 plus Vk minus 1 for each I equal to 1 to k, and A0, which is of the form A0 plus 0, is again a member of A0 plus Vk minus 1, as Vk minus 1 is a vector space containing the null vector 0. Hence, there exists a k minus 1 dimensional hyperplane Hk minus 1 equal to A0 plus Vk minus 1 that contains the given set. It is clear from the last theorem that k plus 1 many geometrically independent points cannot lie in a k minus 1 dimensional hyperplane. The question is, can we get a k dimensional hyperplane containing these k plus 1 many points? The answer to this question is yes, and we shall see that it is not only positive, there exists a unique hyperplane of dimension k containing k plus 1 many geometrically independent points. If A0 to Ak is a set of k plus 1 geometrically independent points in Rn, then there exists a unique k dimensional hyperplane containing this set. Suppose A0 A1 Ak is geometrically independent in Rn. Then the set S equal to A1 minus A0, A2 minus A0 up to Ak minus A0 is linearly independent. So, the linear span of S is a vector space of dimension k. Let us call that vector space Vk that contains S. Therefore, Hk, which is equal to A0 plus Vk, is indeed a k dimensional hyperplane containing the set A0 to Ak. Now, let us suppose that x plus Vk and y plus Vk are two hyperplanes containing A0 A1 Ak, where x and y are 2 points in Rn. Then Ai minus A0 equal to a I minus x minus a 0 minus x, and that is a point in V k. And similarly, a I minus a 0, which is a I minus y minus a 0 minus y, is a point in W k, and this is true for all I from 1 to k. Since S is a linearly independent set of k vectors, it forms a basis of both V k and W k, and this leads to the conclusion that V k and W k are equal. Hence, x plus V k and y plus V k are two cosets of the same subspace V k. It is well known that two cosets are either disjoint or equal. Since the set S is contained in V k intersection W k, x plus V k equal to y plus V k. Now, we get a theorem which gives us the expression for the members of H k. If H k is a k-dimensional hyperplane containing a geometrically independent set a 0 to a k, then any point x belonging to H k is uniquely expressible as summation lambda I a I equal to 0 to k with summation lambda I equal to 0 to k equal to 1. These lambda i's are scalars varying over the set of reals for each I equal to 0 to k. We prove this theorem. Suppose H k is a 0 plus V k, where V k is the k-dimensional subspace of R n generated by the linearly independent set a 1 minus a 0 to a k minus a 0. Therefore, any vector in V k is a linear combination lambda I a I minus a 0 summation over I equal to 1 to k, where lambda I is a real number for every I equal to 1 to k. Hence, any x belonging to H k is of the form a 0 plus summation lambda I a I minus a 0, where summation is over I equal to 1 to k. Now, when x has this expression, it can be rewritten as a 0 plus summation lambda I a I equal to 1 to k minus summation lambda I a 0, where I is varying from 1 to k. So, taking both the terms containing a 0, we get 1 minus summation lambda I a 0 plus summation lambda I a I equal to 1 to k, which we can write as summation lambda I a I equal to 0 to k, where lambda 0 stands for this summation lambda I equal to 1 to k subtracted from 1. So that we get summation lambda I equal to 0 to k is equal to 1. Now, if possible, suppose x has two representations. Say x is of the form summation lambda I a I, and it is again of the form eta I a I, where summation lambda I is equal to 1 and summation eta I is equal to 1. These lambda I, eta I are all varying over the set of scalars R. Then we get from these expressions that summation lambda I eta minus eta I a I is equal to 0, and also from the second expression summation lambda I minus eta I is equal to 0. From 2, summation lambda I minus eta I a 0 is equal to 0, And so, subtracting it from 1, summation I equal to 1 to k, lambda I minus eta I of a I minus a 0 is equal to 0. The linear independence of the set a I minus a 0, where I varies from 1 to k, implies that lambda I is equal to eta I for each I equal to 1 to k. Using this in 2, we get lambda 0 is equal to eta 0, proving the uniqueness of the representation of x. Now, for each x belonging to hk, the scalars lambda 0 to lambda k representing x are called barycentric coordinates of the point x with respect to the geometrically independent set a0 to ak. Now, with these we define a k-simplex which serves as the building blocks for simplicial complex. If a0 to ak is a geometrically independent set of points in Rn, then we take that portion of the hyperplane which contains the points with non-negative barycentric coordinates. That is, we take sigma k as the set of all points of the form summation lambda I a I such that summation lambda I is equal to 1, where lambda i's are real numbers, with the restriction that lambda I is greater than or equal to 0. Then this sigma k is called a k-simplex, and it is usually denoted by this triangle bracket a0 to ak, and these points a0 to ak are called vertices of the k-simplex. So, for a k-simplex we have k plus 1 vertices. We define interior of a k-simplex. Interior of a k-simplex is the set of points of the form summation lambda I a I equal to 0 to k, such that summation lambda I is equal to 1, where lambda i's are scalars with the condition that lambda I is strictly greater than 0. So, if we take a 2-simplex, the geometry of a 2-simplex is a triangle, and interior of a 2-simplex will be the interior of the triangle, not touching the boundary. Now, if we see that 0-simplex is nothing but a point, 1-simplex is a straight line joining two vertices, 2-simplex is a triangle with vertices as the geometrically independent points a0, a1, a2, and 3-simplex is a tetrahedron with the vertices as geometrically independent points a0, a1, a2, a3, and unfortunately we cannot visualize beyond 3-simplex in R3. Now, finally, we define a simplicial complex. Suppose K is a set of finitely many simplexes. We call K a finite simplicial complex if the following two conditions hold. Number 1 is that when sigma is a member of K and tau is a face of sigma, then tau is a member of K. By a face of a simplex, we mean that tau is a simplex with the set of vertices of tau subset of the set of vertices of sigma. Now, if sigma and tau are members of K and sigma intersection tau is not equal to phi, then sigma intersection tau is a common face of sigma and tau. Now, what do we mean by that? That whenever sigma and tau are two members of K, they are two simplexes. Suppose one is a simplex of dimension K and the other one is a simplex of dimension M, then the portion where they intersect, we are not claiming that that has to be non-empty, but if that is a non-empty, then that intersection portion should be again a simplex which is a face of sigma as well as a face of tau. Now, here we see on the left side of the figures, this is forming a representation of the k-simplex, but on the other hand, the right hand diagram is not a representation of a simplicial complex. Why so? That if I take the two simplex and the one simplex and take their intersection, then that is not a face of the two simplex, though it is a face of the given one simplex. It is to note that a simplicial complex is a set of simplexes, not points of Rn. But if we take the union of all the points lying on the simplexes of K, that is mod K is the union of all sigma, sigma varying over K, then mod K is a subspace of the Euclidean space Rn. This subspace mod K is called geometric carrier of K. Now, mod K being a subspace of Rn, it is a metric space, and since any simplex is a closed and bounded subset of an Euclidean space, it is compact and therefore, mod K is a compact space. Now, we shall introduce a typical type of map called simplicial map, which carries the vertices of a simplicial complex to the vertices of another simplicial complex, and it preserves the simplicial structure of the domain. Now, what do we mean by preserving the simplicial structure will be formalized in the next definition. Suppose F is a map from the set of all vertices of K to the set of all vertices of L, where K and L are two simplicial complexes. Then this map F is called a simplicial map if whenever V0, V1, Vq is a k-simplex in K, the corresponding vertices Fv0, Fv1, Fvq constitutes a simplex in L. It is customary to denote the map F from K to L instead of F from the set of vertices of K to set of vertices of L, though F is not defined on the whole of K. Since we do not demand the map to be injective, the vertices Fv0 to Fvq are not necessarily distinct. So, cancelling possible repetitions, Fv0 to Fvq constitute a simplex of dimension which is less than or equal to q in L. Let us take an example. Suppose K is a simplicial complex containing 3 zero simplexes V0, V1 and V2 and 2 one simplexes V0, V1 and V1, V2. And L is another simplicial complex containing 4 0 simplexes A, B, C, D and 3 2 simplexes A, B, C, D and A, D. Then if we take a map F from vertices of K to vertices of L given by f v0 equal to A, f v1 equal to B, f v2 equal to A, then it is a simplicial map because it preserves the simplicial structure of K. On the other hand, if we define a map F from vertices of K to vertices of L given by f v0 equal to A, f v1 equal to B, f v2 equal to C, then it is not a simplicial map, because if we take v1, v2 that simplex in K, then its image f v1, f v2 is actually the simplex BC, which is not a simplex in L. The following are easy consequences of the definition of simplicial maps. First one is that if we take two simplicial maps F and G, one from K to L and the other from L to M, then their composite G composed F from K to M is again a simplicial map. Now, the identity function I from the set of vertices of K to the set of vertices of K, that is, it takes a vertex V to the same vertex V, then it is also a simplicial map. Before we conclude, we point out certain facts, very important facts about simplicial maps. Suppose a simplicial map is given from a geometric simplicial complex K to another geometric simplicial complex L, then it always induces a continuous function from the geometric carrier of K to the geometric carrier of L. The question is, if a continuous function G is given between the geometric carriers of K and geometric carriers of L, then can we expect that G can be obtained from a simplicial map? Of course, this is a very ambitious expectation. It is not always true, but it can be proved that if a continuous function G is given from mod K to mod L, then we can get a simplicial map F from the barycentric subdivision of K, call it Kn, to L, such that the induced map, the induced continuous function mod F from the geometric carrier of the barycentric subdivision Kn to the geometric carrier of L is actually homotopic to the given continuous function G. This particular theorem is known as simplicial approximation theorem.